Assalamualaikum and salam sejahtera. Most welcome to all of you. I'm Cik Zamri. In these short lectures, I will hope you will enjoy it. Today's lesson is about gas law and kinetic theory of gases. But first, we are going to learn under subtopic 13.1 ideal gas equations. There are three learning outcomes as stated below. So for the first one, at the end of the chapter, students should be able to discuss PV graph at the constant temperatures of an ideal gas. The second one, students should be able to discuss VT graph at the constant pressure of an ideal gas. And the last would be students should be able to discuss PT graph at constant volume of an ideal gas. Okay, next, we should understand, so what is gas? Okay, there is a particle of gas inside the container. So what is gas actually? So gas is defined as a substance or matter in state in which it will expand freely to fill of the container, no fixed shape and no fixed volume. And also we should know that the gas particles are widely separate from one another particles, and they are moving freely and randomly. The pictures here show that roughly how they behave. Because most of gases are difficult to observe directly, they are described through the use of four physical properties such as pressure, volume, number of particles, and temperatures. These four characteristics were repeatedly observed by scientists such as Robert Boyle, Jacques Charles, Joseph Gay-Lussac, and many more. Okay, then what is an ideal gas? Gases are complicated. They are full of energetic gas molecules that can collide and possibly interact with each other. Since it is hard to exactly describe a real gas, some scientists create the concept of an ideal gas. So, an ideal gas is defined as one of which of all collision between atoms and molecules are perfectly elastic and in which there are no intermolecular attractive force. Okay, now we can start with our first law in ideal gas equation, which is called Boyle's law. So Boyle's law states that the pressure of a fixed mass of a gas at a constant temperature is inversely proportional to its volume. So that means at a constant temperatures, it relates between pressure and volumes. So that means when the gas is under pressure, it takes less space, the higher pressure, the smaller volumes. Okay, and vice versa. So this equation can be rewrite as a PV equal constant, or any two situation we can apply this equation as P1 V1 equal P2 V2, where P1 is stand for initial pressure, and P2 for final pressure. V1 stands for initial volume and V2 is for final volume. Okay, to check to understand, so look at this picture. This shows a gas stored in a container at 300 Kelvin. What would happen to the pressure of the gas if I increase the volumes of this container? What is your answer? Yes. To find out the answer, please watch the situation. You can observe that the pressure drops when the volumes of the container is increased. Now, if volumes of the container is reduced, does the pressure affected? You can answer me later. Okay. There are two graphs that we can plot, either P against V or P against 1 over V. Both of them shows the same connection between P and V. For P against V graph, it's just like a curve like this. But for P against V over V, it's just a straight line graph. Okay, if the gas temperature is higher, then the graph will look like this, the blue line. Which is slightly different because T2 is higher than T1. Okay, here comes the second law of an ideal gas. We call it as Charles' law. Charles' law states that the volumes of fixed mass of gas at a constant pressure is directly proportional to its absolute temperature. And it's written as a V directly proportional to T when the pressure is constant. Then mathematical equation of the law can be written as V over T equal constant, or for any two cases we normally use V1 over T1 equal V2 over T2, where T1 is initial absolute temperatures and T2 is a final absolute temperatures, and V1 is initial volume and V2 is final volume. Okay, this simulation shows a gas stored in a container at constant pressure 14.7 atm. So I will play this video, so please observe what will happen when the container is heated. Does temperatures increase or decrease? And how about the volume? Yes, as temperature increase, the volume will increase because gas will gain energy and start to pushing container to expand. That's why you see how the volume of container expand in order to remain the same pressure because V is directly proportional to T. Okay, now we are going to discuss the graph of the Charles law. When the graph V against T is plotted, they just show the straight line. This shows that V is directly proportional to T. So that means when T increase, volume also increase. When T drop, volume goes to drop too. Note that negative 273.15 is equal to 0 Kelvin, which is absolute temperature. Okay, now we go to the third laws of ideal gas law, known as a pressure law or Gay-Lussac's law. The law states that the pressure of fixed mass of a gas at a constant volume is directly proportional to its absolute temperature. Or we can write like this: P directly proportional to T when volume is constant. So mathematically equation of this is something like this. It can be written as P over T equal constant, or for any two condition of the gas, it can be written just like P1 over T1 equal P2 over T2, where T1 is the initial absolute temperatures, T2 is the final absolute temperatures, and P1 is for initial pressure, as well as P2 is a final pressure of the gas. Okay, here the simulations of the Gay-Lussac law. This simulation shows gas stored in the container at a constant volume. What will happen when this container is heated more? Do you think the pressure increase? Yes, you are correct. As the heat applied, the temperature will increase. 2. Gas gain energy and start pushing container to expand. But it can, because the container was fixed. Then the kinetic energy of the gas increase and generate more heat. That's why the temperatures increase. Graph of the Gay-Lussac's law. Because P and T is directly proportional, so the graph shows just a straight line. If the temperature in Celsius, it does not pass through the origin. Instead, it cut the y-axis and touch x-axis at the position at the point negative 273.15. This point is absolute zero, and is the lowest temperatures possible. Note that on the Kelvin scale, the graph does not through the origin. Okay, we go next to the subtopic 13.2, kinetic theory of gases. The learning outcome for these subtopics is students should be able to state the assumption of kinetic theory of gases and discuss the root mean square speed or VRMS of the gas molecules. Okay, now we go next to the assumption of kinetic theory of gases. So here's the list of assumption kinetic theory of gases. There are 8 assumptions over there. So to clarify, so please watch the following video.
So there are certain assumptions of kinetic theory of gases. That is, every gas, they consist of extremely small particles. These are known as molecules. Now these molecules of these gas, they are all identical, means they are similar. But if we talk about some other gas, they will be different. So different gas have different molecules, but same gas has molecules which are identical to one another. The molecule of gas are identical, spherical, rigid and perfectly elastic point masses. They are point masses. They are perfectly elastic, rigid, spherical, identical. Now their molecular size is negligible if you compare the intermolecular distance between them, which is order of 10 to the power minus 9 meter. The speed of the gas, it can be 0, it can be infinity, so it lies between 0 and infinity. The distance covered by molecules between two successive collisions, means when they strike one another. So the collisions, so distance being traveled between two successive collision is known as free path. And if you take mean of all these free path, this is known as mean free path. So the number of collisions which is happening per unit of volume of that gas or in a gas is always constant. There is no attractive or repulsive force acting between these gas molecules. When we talk about gravitation, this gravitation to extremely attract or attraction among the molecules is ineffective. Why? Because of the small masses and the high speed of these molecules.
Okay, last but not least, we will discuss the importance of root mean square velocity or VRMS in this chapter. As we know, gas molecules move at different velocities at different temperatures. In order to obtain an effective velocity for a gas molecule, we have to take the value of the root mean square velocity or VRMS instead of average velocities or maximum velocities of molecule. Because at the final stage, we will calculate the kinetic energy of the gas molecule, and we are going to use VRMS. So watch this video for more information.
All right, so we're picking up with this next idea. It's something called root mean square speed, and it's going to take us a little while to get through, so I figured we just start with a new video so that I don't run out halfway through. All right, so little bit of review. Molecules' average kinetic energy is proportional to their absolute temperature, so the temperature in Kelvin. Okay, so in a sample of gas, there is an average kinetic energy, an average speed that we use the Kelvin temperature to measure. Hopefully this is all old school. But remember that that is an average kinetic energy. There are all sorts of speeds of the molecules. Some are moving faster than average, some are moving slower than average. So we've got a lot of different speeds of the molecules. Okay, plus these moving molecules are colliding with the walls, they're colliding with each other. So after these collisions, although we're conserving the momentum because the temperature is not changing, the momentum might not be distributed evenly between the two molecules after the collision, or the wall and the molecule after the collision. So the result is you have molecules in that sample that have a huge range of speeds. So this is where the starting point comes from. So kinetic energy is, or the average kinetic energy is how we measure temperature. But there's a whole lot more going on with the molecules than just that one temperature, that one average speed. So here is a blurry graph. Here is a distribution curve for molecular speeds at two different temperatures. So notice that the blue line is at 0 degrees. You have a much larger percentage of molecules at a low temperature, as opposed to the 100 degrees, where now you have a wider range of molecules, but many more of them are at a higher speed. So what does that mean? The higher temperature molecules have a larger fraction moving, and so the average kinetic energy is increasing as the temperature is going up. So let's take a look at this a little more detailed. So here would be just one graph at a particular temperature showing the molecular speed. There's 3 different points labeled. You got UMP, UAV, and URMS. So the U represents the speed, obviously, but the different kinds, or the way we look at it a little bit differently. So the MP simply stands for the most probable. That's the top of the peak. Makes sense. We don't really worry too much about this one. The AV represents the average speed of the molecules. Okay, and then the third idea is what we refer to as the root mean square speed, RMS. This is important because this speed represents the speed of the molecule whose kinetic energy is equal to the average kinetic energy of all the molecules. So not the average temperature, but the average kinetic energy. They're not exactly the same. So the root mean square speed plays an important role once again because it represents the speed of a molecule with the average kinetic energy. Notice that the root mean square speed is slightly different than the average speed of the molecules. So one more time, here's that first graph that we were looking at. So let's analyze it a little bit more. So the kinetic energy is equal to 1/2 mv squared, or in this case, the root mean square speed squared. Ke is kinetic energy. M is the mass of the molecule. The U is the root mean squared speed. This speed that we're looking at. Okay, the RMS speed is important because as the temperature increases, the root mean square speed is going to increase even though the mass remains constant. So the root mean square speed's going up, more molecules are going to be moving at a slightly faster rate as we increase the temperature, but the mass isn't changing. So that
Until we meet again, thank you for watching. For more information, please consult with your lecturer.